Good morning, everyone. My name is Ilfak Guilfanov. I am the CEO of the Hex-Rays company, the company that publishes the IDO Pro disassembler and the Hex-Rays Decompiler. And today we will talk about the decompiler internals, the microcode. This is a presentation outline. We will discuss the decompiler architecture, and then we will go and check how the microcode is built in the decompiler. Then we will talk about the opcodes and operands. This is the most interesting part of the talk. Then, once we have these building blocks, we can talk about, we will start with stack and registers, and then we will talk about other operand types, and then finally, what kind of things we can do with the microcode. It enables data flow analysis, and because of that, many new analysis types are possible. Then I will tell you about the availability of the microcode and some time for questions and answers if we have time. I don't know. I hope that you've heard about our decompiler. We have a decompiler. It is existing. It has been existing since 10 years now. It is interactive, fast, robust, and programmable decompiler. And it evolved over time. Even in the initial version, that's quite powerful. But over time, we added support for many processors. So we can say that it's a retargetable decompiler. As you see, it can handle 5 processors for now. And you see that it handles native code. It is not a decompiler that handles bytecode like Java or .NET, which is also possible, but we focused on native code. The decompiler runs on top of IDO Pro, and the internals were never really published. So if you wanted to play with the decompiler, you could do so on a high level, but the intermediate language was never documented. And this talk will show you a bit and tell you about this, the microcode. Our decompiler has 6 phases. And in my opinion, it's a very good, very logical steps. First of all, we generate microcode. Then we try to transform it to kind of optimize it. Yes, we use the same optimization techniques as compilers do. We analyze calls, we resolve memory references and other stuff. Then we allocate local variables, generate a so-called C3. C3 is something similar to AST. Then we beautify it because the initial C3 is quite ugly, to tell the truth. And then finally we print the C3 in a human-readable form so the user can analyze it, examine it, and improve. There are some options for that. In this talk, we will focus only on the first 2 steps. If you are interested in the rest, you can check my Black Hat talk. I gave a Black Hat presentation 10 years ago. It explained in more detail all these steps, except the first 2. First of all, the question is, why do we need the microcode? And the answer is very simple. We want to get rid of the complexity of processor instructions. Because all processors have their own special idiosyncrasies or oddities. I will give you just a few examples. For example, the x86 processors have segment registers. The floating point processor has a stack. The ARM processor has thumb mode addresses that have the low bit set, which is ignored by the processor, because if you have an odd address like 13, for example, the function to call is located at the address 12, but the last bit signals to the processor that when performing the call, it should switch to the sum mode. This is a very special thing. I haven't seen something similar in any other processor, and therefore such a thing should not be present in the microcode. The microcode makes the decompiler portable. We can say that we just need to replace the microcode generator and we get a decompiler for a new processor. But of course, the devil is in details, and when I say just, it's just the quotes. Anyway, overall, a decompiler without an intermediate language looks like waste of time to me, because once you finish your decompiler, which never happens, you will have to redo everything for another processor. And we don't want to support only one processor, because there are many of them very popular. Now the question is implementing an intermediate representation or language a difficult thing? Well, your call. How many intermediate languages do you know? Well, there are plenty of them. In fact, LLVM, Rail, binary needs intermediate language, RedDec. Yesterday there were two presentations at Black Hat here, and they were presenting intermediate languages as well. So why do we need one more internal representation? Well, I cannot reply this answer. Maybe it would be possible to use an existing one, but for us, the reason was that I started to work on the microcode and the decompiler really long ago. It was in 90s. I don't even remember the exact date when I decided to create microcode. And that's the main reason why Hex-Rays Decompiler has its own intermediate language. So I started in around 98, and well, I am very bad with names, so I decided, okay, it's called microcode. Why is microcode? Because every instruction, every processor instruction is split into multiple micro instructions, and one micro instruction does one thing, no side effects. It's a very simple thing, and that's why the name microcode looked logical to me. Naturally, it is virtually impossible to design something from scratch and get everything right. Some design decision turned out to be bad. For example, we have a notion of virtual stack registers. Well, a design decision that is taken at the early stages is really difficult to fix later, because there are many so much code relies on it, on this concept, and implicitly assumes that we have virtual stack registers. Well, on the other hand, I am happy to tell you that virtual stack registers will disappear in the future. Microcode continues to evolve, and we continue to modify it, but once we publish, in fact we already published it, we will not modify it anymore. At least we will try not to modify it. So what were my design goals when I decided to create microcode? The first and the most important thing is simplicity. We already work in handling very complex things, so the simpler we make it, the easier will be in the future. As you will see later, you will see that I failed at this task, but it is because the real world is really complex. But anyway, at the beginning, what do we have when we start from scratch? We have no processor-specific stuff, one instruction, one microinstruction does one thing, and there are very limited number of instructions. There were only 45 in '99, but today we have 72 instruction opcodes. It's just because we had to support floating point arithmetics and other fancy things. In fact, what is good with the microcode that it really can handle real-world programs. And initially, we started with simple instruction operands. Initially, we had registers, constants, and memory. Well, by memory, I mean the global variables and stack variables. And I decided that we consider only compiler-generated code, because when you talk about handcrafted assembler code, anything can happen. You cannot trust even a disassembly listing, not to talk about microcode or decompiler, because it is possible to modify things that when you read the listing, you see seems innocent looking instruction like move, but in fact, when this instruction is executed, there will be an exception happening, and the exception handler will do something else, not move. So you read the code, you see instructions, but they do not mean what they look like. Another thing that we don't care about, the timing. Since we will optimize the microcode and throw away non-interesting dead code, then timing will change. Therefore, no need to even try to preserve anything. The instruction order, we decided not to keep, not to preserve it neither. It is just impossible, in fact. And order of memory accesses, we will not care about it neither. So the easiest thing, I think, that just to show you how it looks like, let's take these 4 instructions. Very simple x86 instructions. Apparently, we access memory. We read from EBX plus 4. Apparently, it is a pointer because the next thing we do, we read a byte from EAX plus 1. Then we subtract 61. And if it's 0, then we jump somewhere else. Apparently, it is a fancy way of comparing DL against 64 hexadecimal. Let's look like what will happen, what kind of microcode will be generated for that. That's it. As you see, out of 4 instructions, we got 20 instructions. And on the colon, just right to the semicolon, you will see the addresses of the original instructions. For example, the instruction at FB got translated into 5 micro instructions. And the instruction at 501 got translated into how many of them? 7? 7 micro instructions. You see that all side effects are spelled out explicitly. It's very verbose. So we cannot present this to a human being because it's not that readable, not very nice to handle. Anyway, what we'll do, the next step, we will try to optimize it a bit. We will throw away anything that is that won't be used. We will remove the dead code. And then we end up with only 9 micro instructions. Another thing that we did with the microcode is that we propagated some instructions into another instructions. Take, for example, the very first instruction here. It's LDX, which stands for load from memory. It loads from the memory, and the offset is specified as EBX plus 4, which is an addition instruction. So the addition instruction got propagated into LDX. This kind of makes the microcode slightly more complex than initially, but on the other hand, it will allow us to represent things nicely at the very end, when the decompiler will finish its work. Let's continue. There will be further microcode transformations. I will not stop at them in detail, but what we will have, we will first have 3 instructions, and finally we will just have one very long micro instruction. This micro instruction does not really deserve its name anymore because it's not a micro, it became very, very complex instruction, but on the other hand, it has a very nice feature of being translatable into C3. So if we translate it into C3, we will get a very nice if argv. Apparently, the initially the EBX contained a pointer to it was argv. Then we just say that if argv11 is equal to A, then we do something. Well, I'm sorry that reading microcode is not easy because it was not one of the initial design goals. As you see, all operand sizes are spelled out explicitly, and well, the initial microcode was simple, but then it became quite complex. So the translation from native processor instructions to micro instruction have been implemented in plain C++. For now, we don't use any automatic code generations or machine description to generate them. Maybe it's a good idea, but so far I don't feel that we are ready for that. Now I will just go quite, well, hopefully I will go quickly and tell you about the possible instructions that exist in microcode. As you will see, they are quite straightforward. And on the other hand, these 72 opcodes cover all current needs that we have with real-world programs. So the first group is the 2 instructions. They just move values from one place to another place. In fact, we have here L and R, left and destination operands. In fact, all micro instructions have 3 operands: left, right, and destination. Don't ask me why it's called left, right, and destination, but okay, this is like this. Here we have load constant and move instructions. Nothing fancy. To represent real-world programs, we need to be able to work with parts of instruction, parts of registers, read or write only 1 byte or part of the double word. Therefore, we need to change the operand size. For that, we have 4 instructions. Extend sign or extend with zero fill, and take low or high parts of an operand. And here, as in any other instruction, the left and destination operands can be anything. It can be register, it can be stack, it can be global memory, or even more complex things. There are only 2 instructions that work with the memory initially. We have store to memory and read from memory. They denote the memory allocations by using a pair of a selector and offset. This will allow us to handle segmented memory if there is if we need to do so. So far, we were using only flat memory model, so this feature of microcode was not really used, but it is there for the future. We have a very natural and standard set of comparisons. They compare the left operand against the right operand and put the result in the form of 0 or 1 into the destination operand. So these instructions are used mainly to generate processor condition codes. And the destination register is usually something like a carry flag, 0 flag, and so on, but we don't really limit them to the predefined set of registers. So therefore, even PowerPC, for example, with its 4 sets of condition codes, can be handled very nicely by the microcode. Then we have a natural set of arithmetic and bitwise operations. Nothing to say here. The shifts, we have only 3 shifts and no rotations. The rotation operations existed initially in the microcode, but later we decided to throw them away because they turned out to be useless. We cannot represent them nicely in the C language, and since our target is C, then it was not really interesting to have them. Nevertheless, the microcode can represent rotations using so-called helper functions. I will show you later. We have the following group of very fancy and odd instructions. They are necessary to precisely track the carry and overflow bits after arithmetic operations like add. For example, we have a pair of instructions like add and then ADC. This pair is used very often to to implement 64-bit operations on the 32-bit platforms, or even to implement 120-bit, 28-bit operations on 64-bit processors. And to be able to correctly represent things, we need these odd instructions. Normally, they get eliminated during microcode transformations. Once we detect that add and ADC, they come in pair, we will combine them into one big addition instruction, and CF add, for example, will simply disappear. Then we have control flow instructions like indirect jumps, and go-tos. Indirect jumps normally should go away after some transformations. If not, then it's bad luck, because in C language there is no counterpart, there is no nice way of representing indirect jumps. The calls, there are 2 different instructions for them, direct and indirect calls. There is a very tough problem with the call instructions, because when we have a call native instruction, we don't know what is the calling convention, and we don't know where is the return value, and this is one of the biggest problems during reverse engineering, during decompilation, to determine them. And if we are lucky, we call a well-known function like close handle, create file, then we know the calling convention and everything. If not, the decompiler will try to guess this information, the calling convention and the call arguments, and all this information will be stored in the D operand, and at the bottom of the slide you will see that how we represent the call instructions. You see that there's a lot of detail here, and this detail is enough to represent again all real-world programs, but almost all, because recently there was someone complaining about our decompiler not being able to handle some Rust language constructs, but we will fix that in the future. The next group is the conditional jumps group. They are similar to the instructions that were generating kind of processor condition codes. So we have a jump, very standard set of jump 0, jump not 0, great, and so on and so on. Maybe the first and the very last instructions are somehow special here. Jump conditional means evaluate the left operand, and if it's non-zero, then take the jump to the destination. And jump table is used to represent the switch idioms in the output. Initially, we had no floating point operations, but since our goal is to be able to represent real-world programs, then we had to add the necessary stuff. As it turned out, it's not that big. You see, we just need a few conversion instructions and a few arithmetic operations. Four operations like add, subtract, multiply, divide, negation, and that's it. The rest, like built-in functions like cosinus or logarithm and other things, can be handled using so-called helper functions. I will show you later, hopefully. And finally, we have some, the last group, it's called miscellaneous. The most interesting instruction here, I think that it's the external instruction, because some processor instructions cannot be expressed in microcode. Take something like load interrupt descriptor or system call or other things. We don't, let's say, square root. We don't have microcode instructions for them, and they are represented either using so-called intrinsic calls or helper calls or the external instruction. The external micro instruction just tells us that there is something that we cannot express in the microcode, but it helps us to trace the data dependencies. So we know, for example, that AAM will use, is it AX or AH? I think that it uses the AH register and modifies AL. I don't remember what AAM does. But anyway, it just allows us to trace the data dependencies. And we also, the instruction called undefined is used to represent, to express the fact that something is spoiled in a way that we cannot predict or describe. For example, the zero flag after multiplication is spoiled. That's it. You see that it was not that fast, and we have these 72 instructions. Maybe we should extend it a bit, but I don't feel the need right now. It looks good, and I think that it will stay like this for a while. So now let's switch to the operands, because I discussed the instruction, of course, but I did not show you what they operate on. Well, if you take as everyone else, initially we had only two things, numbers and registers. It was very simple, because we take a register, we put a value into a register, we know that it won't go away, it won't disappear, it won't be changed by someone else. In other words, only direct accesses are possible, indirect access to registers are not possible. And therefore it was very simple to analyze things. But the reality is much more diverse than that, and we had to add a lot of new operand types. Logically, we started with stack variables, then global variables, and addresses, a result of other instructions, and so on and so on and so on. The list is not exhaustive here. There are much more operand types than the slides shows. But anyway, just I will stop on some of these operands, and then we'll discuss how microcode can be used. The register operands. If you work with x86, you know that it has a very funny way of funny register set. We have EAX, it has parts of EL, EH, and it's quite difficult to work with them. We don't want this kind of mess in the microcode. Therefore, all of them are mapped to microregisters. For example, AAX is mapped into 4 microregisters. One microregister is 1 byte. And this mapping is very straightforward, very simple. It can be done forward and backward. We can go back from microregisters back to processor registers, and it helps to understand the code. And usually there are more microregisters in the code then processor registers, because we can allocate them as needed when we generate the microcode. Once I implemented the very first version of the microcode engine and added some rules to simplify it, to optimize it, well, it was natural that they work with registers. Like, for example, XOR AX, AX, it is the same thing as putting 0 into EAX. And I had no logic to work with the stack variables. And I was lazy and decided, why not just map the stack frame to microregisters? Since we have unlimited number of microregisters, we can just consider them as the same thing as well, stack variables as microregisters. Initially, it helped a lot because I did not need to re-implement or improve the existing optimization rules, but later it kicked back and it bit me because there were many problems with the stack variables, like indirect references to the stack frame, and therefore a stack variable cannot be considered as the same thing as a register. It can be modified by someone using a pointer. So we had to live with that for a while, but finally I can tell you that we fixed the problem, and now the bad design decision will go away. Just to explain you in more detail where the problem is. This slide shows the stack frame of the typical stack frame of a function. The red areas are the ones that can be modified indirectly. And therefore, we cannot really reason about them. And we should not consider them as the same thing as virtual registers, as microregisters. You see that in the middle of this diagram, we see the return address. Just below the return address, there is a red area where we have saved registers and local variables, and beneath it we have unaliasable local variables. Therefore, we have to handle these red and yellow areas in a different way. For the yellow area, we can reason about the variables. We can perform data flow analysis. While for the red area, it is also possible, but we have to remember that any value that we stored there can be modified indirectly. The initial stack, registers and constants, these three operand types, they were not enough, of course. Very soon I had to add standard pairs like EDX and EAX. I was lazy to do so, therefore I just mapped EAX and EDX so that they are adjacent as micro-registers, and instead of having two separate 4-byte micro-registers, I ended up with a big 8-byte micro-register. But compilers get better over time, and modern compilers can use any registers as a pair, not only a fixed like EDX and EAX. It can be anything. It can be even a stack location plus a register. So a value is stored in two different places. The high part is stored in the location pointed by SP+4, and the low part is stored in a register. And the compiler can handle it nicely. Since compilers do this kind of nasty things to us, we had to introduce a new operand type for it, so it's called operand pair. It exists, it consists of two halves, low and high part, and these halves can be located anywhere, stack, registers, or global memory. Well, in fact, this is not enough. Since we want to represent real-world programs, it's not we have to represent real things that are used by compilers. With in the 64-bit world, there's the ABI that is defined on one hand, in the 64-bit world, we have a better situation because we don't have nightmare of calling conventions. Everyone follows a calling convention that is specified in the ABI. Well, there's a slight problem there because Visual Studio on Windows and GNU compilers on Linux, they use different calling conventions, but it's not a big problem for reverse engineering. But these ABIs, they introduced very complex rules to pass structures and unions to and from the functions. For example, we have a structure. It is only 8 bytes. So in theory, it can be passed on the register. And yes, that's what the compilers do. They put the entire structure into a register. But sometimes they do even nastier things. They pass part of a structure on a register and the rest on the stack. Let me show you an example. Here we have a structure. It's only 8 bytes. It has 2 parts called the division result. It's a quotient and remainder. And we have the division function. It accepts 2 values and divides them and then returns the result in one register. This is a nasty thing. If you look at the assembly code, you will see that there's after the call div, we have move sign extended double word. Then we shift the the quadro word in REX by 32, and then we extract the low part, the second part. To represent this in a nice way in the output, we need to have scattered operands. It's a scattered operand is an operand that can have its parts scattered over different places, various places. It can be registers or stack. So you see that the output is quite nice. We have the result of the call is put into a variable called v2, and apparently v2 has is a structure, and it has 2 fields, the quotient and the remainder. That operand, the scattered operands turned out to be quite complex things, and we do have support for them, but not everything can be handled nicely. We are working on it, but we are not there yet. Okay, enough of these minor details. Let's talk about what we can do with the microcode and how the decompiler uses the microcode. First of all, the microcode, as you see that the generated microcode was very verbose. Then we perform the initial pre-optimization step that uses a very simple constant register propagation algorithm. It's very fast and gets rid of most temporary registers, reduces the microcode by 2 because it also removes unused instructions. And then later we will use another algorithm that will propagate partial registers. For example, we can propagate EAX into an expression that uses only part of it. It can move one instruction inside another. It can work with all kinds of operands. First, we do all these optimizations on the basic block level, and then we build the control flow graph and we will to perform the data flow analysis. For that, the result of the data flow analysis is represented as use and define chains. So these chains, the use def information, can later be used to do many things with the microcode. We can delete the dead code. For example, it's at the beginning of a function, we put some value into a register, but this value is never used in the functions, and we can delete it from the output. We can propagate operands, and we can generate assertions. Let me show you the assertions. Imagine that we have a conditional jump not 0. If EAX is not 0, then we jump to the block number 5. Otherwise, we don't jump. We just continue to the next block. Graphically, it can be represented like this. We have two arrows, true and false. And if we don't jump, then we can deduce that EAX is 0. Since we did not jump, it is 0. So what we do, we generate an artificial instruction that moves EAX 0 into EAX. That instruction was not present in the native code, in the initial code that in the input, but since we explicitly put it there, then it can be propagated, and EAX will be replaced by zeros in this block and maybe in other blocks as well. So this is a nice trick to be able to propagate constant values over basic blocks. We have really literally hundreds of very small and sane optimization rules. For example, if you have x minus y plus y, it is the same thing as x. Please note that this does not depend on the compiler. We don't care if it's a GNU compiler or a Microsoft Visual Studio or anything else, or LLVM. All these rules, they work regardless of the compiler. And I'm happy to tell that let's say virtually all transformation rules that we apply to the microcode are rules like that. They are sound, they are simple, and therefore we are quite sure that the output will be correct. Of course, there are some places where the decompiler has to guess. For example, the calling conventions, the call instruction, and there if you guess it wrongly, then the output will be wrong. But this is an unsolvable problem, and we just provide ways of for the user to fix these things that the decompiler does not need to guess, but just uses the information provided by the user. We have also more complex rules. For example, the following rule recognizes 64-bit subtractions. You see that it is quite complex, and it is what do I say? It looks complex. The description looks complex, and believe me, the implementation is complex as well. So we implement such a rule in C++, and it is big, but on the other hand, it works very fast because of that. We have tons of rules like that, and they work like little ants, every rule doing its simple job, and the end result is, for me, it's bigger than the sum of elements. It is bigger, and it allows us to provide a very, very nice output, very human-readable output. On the other hand, one more thing that why our rules are more complex, because take for example this rule, CMB 43, it tries to combine two parts of a multiplication and generate an 8-bit multiplication instruction. There we have two instructions, multiply and low, and the low instruction, and between the low and multiply instructions there can be many other instructions. The only requirement is that they don't spoil or modify x and y, the operands that are used in our pattern. How do we do that? We don't naively check what is the next instruction after mul. Instead, we rely on data dependencies. We go and try to find where the low instruction is. We have also interblock rules. They work on multiple blocks. You see that if you have 3 comparisons with some relationship between them, it can be collapsed into one simple comparison that jump if it's lower between x and y. Another rule, another example, division by power, signed division by power of 2. We divide instead of division, instead of 3 blocks, we just make it just 1 block. One instruction. Now all these things I explained to you about these rules, microcode, operands, and so on and so on. What is the interesting thing for you here? The interesting thing is that you can use all these microcode and the transformation rules because you can implement plugins that would examine microcode, find interesting things, and you can even improve things by adding your own rules, by hooking your rules to the optimization routine. Well, the SDK has some samples explaining how to do that. For example, we have an ARM decompiler has a rule that converts in the indirect jump into return, but for that we need to prove that LR is the same as the LR at the beginning of the entry point. We can do that by using the data flow analysis. Okay, therefore I have to tell you just a bit about the data flow analysis. You notice that to the right of the instructions we have U and D lists. U means list of locations used by the instructions, and D means defined by the instruction. And these lists are maintained for you by the decompiler engine, and you can use them in your analysis. First of all, we have this list for each instruction, for each block, and more than that, we have even may and must and may access lists for each instruction or block. And these lists are very, very useful because they help us to answer questions like, is the defined value used anywhere? If it's used, where exactly? And so on and so on and so on. Therefore, if you use a microcode, you can really answer questions like that, and therefore analyze things. Well, I think that I will skip these slides because I lack time. Sorry. Just a few words about the microcode, the testing, and so on. We really try the microcode to be reliable and powerful enough to express real-world programs. Therefore, we test the microcode extensively. We have a small farm of tester computers running all the time and checking if we have any bugs. By the way, we have very little reports about microcode, about the decompiler in general, because I think that it's thanks to our testing techniques. But anyway, if you find anything about fishy about the microcode, just send us a message. We are happy to fix things. We really hate the bugs, and we try to get rid of everything. Anyway, The microcode is available, the API is available. It's only C++ for the moment, but the Python will come very soon. I think that if not this year, the next year you will have the Python API, and I hope that we will show you some interesting things that you can do with the microcode API. We will blog about it. Anyway, if you have any remarks or anything, feedback about it, just send us a message. Or I think that I ran out of time, so therefore the questions will be in another room, right? Okay. Thank you for your attention.